The following molecules are, and then we have a list of options: identical, enantiomers, diastereomers, or constitutional isomers. So we're being asked to compare these two molecules and see if they're the same as each other, if they are mirror images of each other, if they're diastereomers, or if they're connected together differently. So I think the first thing to do in approaching this would be to number the carbon chain in each case to see that you've got the same groups in the same spots. So either way you number this chain, you're going to have alcohols at carbon 3 and 4. So we can just number this. And we can see that we have that same connectivity in our other structures. So both of these represent 3,4-hexane diol. Okay, so diol because we have two alcohols, 3 and 4 to indicate on which carbons those alcohols are located. And so what we want to check next, I'm noticing something about this structure here on the right. And what I'm noticing is that we've got this plane of symmetry. So we do have chiral centers, but if a molecule has chiral centers but has a plane of symmetry, this molecule is not chiral. So the plane of symmetry makes this achiral. So the question is this also the same? Is this also an achiral structure? So we want to recognize is that when we're dealing with these zigzag structures, that you have your molecule in a staggered conformation. And what you might not realize about these sort of Fischer projections is that this is actually an eclipsed conformation, which is how we're able to see that plane of symmetry. Because when you're looking at this, we need to remember that our horizontal bonds are sticking out at us, and our vertical bonds are facing away from us. Right, so if you were to kind of turn this over and look at it in a projection like this, then you would see that you have that plane of symmetry. You'd see that this is an eclipsed conformation. And so if we want to take this and see and check for an internal plane of symmetry, we want to rotate. And I want to rotate a bond around that carbon 3,4 bond because that's where I see that plane of symmetry. So what I'm going to do is I am going to rotate this center bond down. So what I'm doing is I'm pulling this group down. So I am, just to show this rotation, so we've still got that OH where it was. And here's the bond between 3 and 4. So if I'm pulling this down, I'm going to end up bringing this group down, right? And it's going to push these up. And when these get rotated up, if you actually have a model and you rotate it, you'll notice that the alcohol is going to switch from sticking out. When you rotate the bond, that's going to be going back into the plane. And this is also sticking out. The hydrogen also switches places, I should say. And so now it's switching out. So we're not breaking bonds here. We're simply taking that bond and rotating it. Okay, so you're rotating it 180 degrees essentially to put it into this eclipsed conformation. And then you have this internal plane of symmetry. Okay, and so if you can see this at this point, that's fine. I'm going to try one more thing, and this may or may not help you because I'm going to go ahead and I'm going to put this in a Newman projection and rotate it. So it really depends on how comfortable you are with Newman projection. So I'm going to draw my Newman projection. My little eyeball here, that's a badly drawn eyeball, looking down this bond. So if I look at that, I'm going to see the ethyl group, and I'm going to abbreviate that ET. I'm going straight down. I am going to see the alcohol going to the left because it's in the plane of the page, and the hydrogen sticking out of the plane. And then on that back carbon atom, I'll see the ethyl sticking out. I'll see the alcohol sticking down and to the right, and I'm going to see the hydrogen down and to the left. So this is this conformation. So what I'm doing when I'm going from here to here is I am rotating so that I get everything eclipsed. So I'm actually rotating 180 degrees. So we will rotate this one also 180 degrees. And so I'm gonna hold that front carbon steady because I'm gonna do the same thing I did here and rotate around that carbon 3 to 4 bonds. So when I do that, nothing changes on the front carbon. But so we wanna think about where these groups are gonna end up. So that means that this ethyl group is gonna rotate so that it's all the way down where that one was. This alcohol is rotating 180 degrees and the hydrogen is also rotating 180 degrees. So hopefully that's not too confusing, those errors, but when we do that, right, so we're bringing that ethyl group 180 degrees down. So it is now overlapping with the ethyl group on the front. As we do that, the alcohol also moves 180 degrees, so it's now eclipsing with this alcohol group. And the hydrogen is also, because we're moving this whole thing all at once, shifting it around 180 degrees. This hydrogen is also going to be overlapping with that one. So now you can see that you have a plane of symmetry. So this is your eclipsed conformation. Both of these are. They represent the same molecule. So you have a plane of symmetry. So this is also not chiral. So what we have here is these are meso compounds. Right, so meso means that you have one or more chiral centers, or more than one chiral center, but you have an internal plane of symmetry, so it is not chiral. So the way that you would actually name this, because you do have chiral centers, you might say, well, which one do I do? Do I name it R, S? The way that you name this is you would actually name it as meso, and that communicates, oh, we're dealing with the symmetrical one. So it would actually be meso 3,4-hexane diol. But what we really want to recognize in this question is the fact that these two molecules are identical.